So we're going to be solving problems today involving the speed of sound. We're going to be looking at what's called resonance, mechanical resonance, and also acoustic resonance. And we're also going to be looking at beat frequencies. And these all have something to do with sound. Although mechanical resonance is not directly related to sound, when we study mechanical resonance, we take a step further with what we learn and say, oh, that's the same idea as acoustic resonance, which has to do with sound. Mechanical resonance has to do with physical objects, not air. Acoustic resonance has to do with air. I want to show you a couple of demonstrations in today's class, but I also have to be aware of the time because I have to leave here at 20 to 11 to go for an appointment. So Mr. DeRose will come in during the last 20 minutes of class and just be in here while you're working on the assignment. So let's get started here. The speed with which any mechanical wave moves is determined by the medium it moves through. We talked about this. It was the most difficult thing for you as a class or you as an individual to come up with an answer to. What determines how fast a wave travels? And it turns out it's whatever it's traveling through. And I kind of alluded to that a light wave, when it's traveling through air or space, travels with a certain speed. But if that wave enters water, it travels slower. Okay? So it's the actual substance that's vibrating, and I'm saying substance here because although I just talked about light, this statement is mechanical waves. This statement is about mechanical waves. So it would make sense then that how fast air carries a sound wave is determined by the properties of the air. And it turns out that at a higher temperature, sound will travel faster, which is a little counterintuitive. But at a higher temperature, all of those air molecules are already bouncing around randomly very, very quickly. So all of those air molecules have a lot of energy. As soon as I cause a disturbance in that section of air, I'm pushing them in a particular direction, but many of them are already moving in that direction quite quickly. In other words, can you appreciate that a sound wave is a domino effect going from the air right next to my mouth, eventually leading to the air right next to your eardrum? We've talked about that before. Well, there's a time delay between when the collisions occur, but if the molecules are moving faster, the collisions will occur over a shorter period of time. The wave will travel faster. Now, it turns out that at 0 degrees Celsius, there's other factors at play, like altitude, for example, but just maybe at sea level or at Wetaskiwin level. At 0 degrees Celsius, that's the speed of sound. And it turns out for a limited range of temperatures, the speed of the sound increases by 0.6 meters per second for every degree Celsius increase. And I say for a limited range because I think once you get to quite a high temperature, you probably have a different mathematical relationship. So this is a formula that we can use to determine the speed that sound travels at in air. And in this formula, T is the temperature of the air in degrees Celsius. Pretty straightforward. This is not on your formula sheet, but it is something that would be given to you in the context of answering a question. So you know when you're writing exam questions and you have that context box and it gives you all of this information, this would be given to you. So to start off with, a very, very simple question. What is the speed of sound in air at 25 degrees Celsius? Well, the formula is the speed of sound is equal to 331 meters per second plus 0.6 multiplied by the temperature. And that's all we're doing here. What do we get? We get V equals 331 plus, I want to say 15. So that extra 25 degrees Celsius adds 15 meters per second to the speed of sound. And by my count, that gives me 346. Okay. And that would be in meters per second. I don't know if we're going to do an example dealing with what I want to talk about briefly, but I would assume that if I told you the speed of sound, you could find the temperature. I think that's a reasonable assumption. That if I told you in a particular situation sound is traveling at 300 meters per second, what is the temperature? Then you would put 300 in for V and you could solve for T. Right. One more. How long does it take sound to travel 2 kilometers through air? I guess this is a question you could answer or could have answered yesterday or even the day before, because this has nothing to do with the temperature. And in retrospect, I'm not sure why I made the question this way. So I'm going to change this question. I'm going to change this question. I'm not going to give you the speed of the sound. And the speed is not going to be this number. I'm just going to make something up. How long does it take sound to travel 2 kilometers through air at a temperature of 80 degrees Celsius? Okay. Do you get my drift here? That I'm not quite sure why I made this example in this lesson. You already knew how to do it. So this is just a case of what we talked about at the beginning of class before we started the lesson when we were reviewing wave motion. Yes, you can use the universal wave equation, definitely, but you can also use speed equals distance over time. It's uniform motion. So if we want to find the time, we can make an itemized list here, speed, distance, and time. The distance is 2,000 meters. If we want to find the time, I hope you're okay with 2,000 meters. It's 2 kilometers. If we want to find the time, then you need to know the speed. So we take just a little detour off the road for a second. It's a really minor one. And we can find the speed, I'll even put it up here, by using that formula, 331 plus 0.6 times the temperature in degrees Celsius. And by my calculation in my brain, I'm getting 379, and I'm seeing a couple people nod, so that's good. It's a pretty basic question now. I'm going to choose to rearrange this formula first. T equals D over V. So I can take that 2,000 meters divided by 379 meters per second. It's going to be somewhere, I'm guessing, between 5 and 6 seconds. 1, 2, 3 divided by 379, 5.3 seconds. Are we okay with that? Okay, we've advanced we've come very far in this course. If you go back and you look at the first couple of weeks, some of the math we were doing and the problems we were solving were a little terrifying at times. Okay, it was quite complicated, but you become more and more accustomed to generally working with formulas. You have all kinds of things floating around here in terms of formulas. And I'm just pointing out at this point of the game that with regards to what we're talking about today with the speed of sound relating to the temperature, I could ask you questions where I give you some information and ask you to find the frequency of the sound at a particular temperature. Or I could give you the frequency at a particular temperature and then ask you to find the wavelength. And you'd have to use the formula with the temperature to find the speed and then the universal wave equation. You get the idea that it can be a little bit of a treasure hunt here in terms of, or a scavenger hunt maybe is a better expression, in terms of solving these problems. And we're certainly not going to do every kind of problem in this lesson. All right. So now we have a different question. And this is maybe more related to still the temperature, but it's connecting now the V equals F lambda. A tuning fork has a particular frequency. What is the distance between successive compressions of the sound wave if the temperature of the air that the sound wave is moving through is 25 degrees Celsius? So not only are we going to have to use the universal wave equation here, and we're going to have to use this formula. We're going to have to understand what this is. I don't mean what it's equal to, although that's the goal of the question. We need to understand what it's asking us to find. And for a sound wave which is longitudinal, the distance from one compression to the next, and that's what successive means. It means one to the next. Okay? Successive years are 2024, 2025. We need to understand that what that is the wavelength, which of course is lambda. So it's just a two-step problem here. You're going to have to, first of all, well, I don't know, first of all. I'm just going to say that you need to find this. I'll say first. The reason why I'm hedging on that is you could build a single equation and just not worry about first or second. You could just do algebra. But we're going to have to find the speed of the wave first. Once we know the speed, then we can find the wavelength second. So what will we get for the speed? Pretty basic calculation, 331 plus 0.6t. Oh, didn't we do this already? Wasn't it 346? You get 346 meters per second. Now we can go into the other equation, the universal wave equation. The wavelength will be the speed over the frequency. So the wavelength is going to be 1.3. I'm just guessing. Well, I'm not really guessing, I'm estimating 1.4 meters. So let me write this down first. You know, if I have a tuning fork was that 256? Well, I'll lie to you and say this is 250. Yeah.
I use 364 instead of 346.
Can you repeat that, please?
You use 364 instead of 346.
Oh, thank you. I'll just put in the units this time. Thank you very much. I wrote down the wrong number, and it was 256? Okay. See, I told you it was 1.3. No, I'm just kidding. It rounds actually to 1.4, but it's important that we carry the right number through. So if it were to 3 digits, we would record 1.35. Thank you, Sukhman. 1.4 meters. So I'm not going to lie to you. This is not a 256 tuning frequency Hertz tuning fork, and I just don't feel like walking to the back of a room and get one. But if this was, what that means is as this sound travels outwards from the tuning fork, if you could see the air, you would see patches of air that are squished together. And the distance from one squished together compression patch of air to the very next one would be 1.4 meters, but you would never be able to trace it because they will be moving through space at 350 meters per second, roughly. It's a hard thing to imagine. And you have to imagine it because you can't see it. You have to try to visualize it mentally. Any questions with 3? All right. There's this thing called resonance, and I'm trying to be aware of the time here because I have to leave in a half hour. If I have a tuning fork with a resonant frequency of 128 hertz, it produces a sound wave with that same frequency. I could answer that by saying because the frequency is determined by the sound. But the bottom line is, if that tuning fork has a resonant frequency of 128, resonant means natural. It means when you hit it, that tuning fork is going to vibrate back and forth 128 times per second. And you cannot change that unless you change the tuning fork. I mean, you could put a couple of pieces of gum on the ends of the tuning fork. That would change the tuning fork. The frequency would be different. But otherwise, it will be oscillating at 128 times per second. The reason why it produces a sound wave is there's a physical contact between that tuning fork and the air. Just like if I tap my toe in and out of the water with a particular frequency, I will force the water up and down with that same frequency. If this tuning fork is tapping the air 128 times per second, the air will move back and forth 128 times per second. So really, it's because there's physical contact between the tuning fork and the air. And air is a very flexible material. I mean that in a physical and a kind of an analogous sense. Air can oscillate back and forth at many frequencies. 128, 256, 256.1587, and your eardrum does not have a single natural resonant frequency. It can oscillate back and forth at a range of frequencies, which is why we can hear a range of sounds. But if I had a tuning fork with a frequency of 10,000 hertz, I'm going to say most, your ear cannot oscillate at that frequency. So if I could have a tuning fork with a frequency of 10,000 hertz, or an audio generator that created that frequency, you wouldn't hear it. A bat might, a cat probably would, and maybe a dog would. We have different ranges of frequencies. All right. Resonance is the process of having one object which has a natural frequency in oscillation causing a nearby object to oscillate with the same frequency because it matches its resonant frequency. Okay. And whether it's through acoustics, which means sound, or physical contact, which is something different, there's a contact being made between the thing that's oscillating and the thing that's oscillating later. It's a physical contact through the air or maybe the ground. So resonance is the process of one object vibrating with its natural frequency, resulting in a nearby object vibrating with the same frequency. I started off the unit by talking about this, that I had an old car, a 1990 Tempo. And when I got to, I think it was about 106 kilometers per hour, that would be a frequency of vibration of the engine parts and the tires all moving. And it turned out that I had a resonant frequency of my dash as being whatever that frequency was as well. So at that speed, my dash would start moving up and down very, very quickly. But if I went a little bit faster, it would stop. If I went a little bit slower, it would stop. We refer to this as mechanical resonance. Two objects physically in contact with one another. If you were to go to the front page of your unit handout, there's a cartoon there. It's from a science mathematics web-based comic strip called XKCD. And somebody, I believe, is tapping their foot or shaking their foot. And nearby on somebody else's desk, their desk is rattling. And depending on how quickly not how quickly, depending on what the frequency is of the foot tap. In this particular case, it's matching the resonant frequency of the person's desk. So there's a mechanical resonance. Very quickly here, I don't know, and we're not going to look at the whole thing. There's a bridge that was constructed in, I think, the 50s, 1950s, so a long time ago. I think in Washington. It's called the Tacoma Narrows Bridge. And when they were constructing the bridge, they noticed that the bridge would sway in the wind. And everybody kind of, I don't know why they didn't say, hey guys, maybe we should rethink what we're building here, okay? But they didn't. Everybody involved said, oh, that's interesting. And they even nicknamed the bridge Galloping Gertie. I don't know why Gertie. And it turned out that the bridge, like a guitar string or like anything else that can vibrate, had a resonant frequency. And when the wind went through the openings between the cables at a particular speed, it created a frequency of vibration of the cables which matched the resonant frequency of the bridge. So this is what the bridge was doing. There's actually somebody on the bridge there. Legend has it that that person left their car is over there, and they knew they were in trouble, and then they went back and they tried to, there was a dog in the car, they tried to save the dog, and I'm sorry, the dog didn't make it, okay? But that's what happened due to a resonant frequency, and it eventually collapsed. And I don't know why they have really good video of everything going on, and then it just cuts and they show the bridge in rubble. So they didn't actually capture the video of it collapsing. That's an example of mechanical resonance. That's pretty amazing because you think it's made of concrete, right? Concrete and asphalt. I'm really disappointed that no video exists of this with audio, because I would be interested to hear what it sounded like. With all that stuff twisting and whining, it must have been amazing. Anyway, that's what happened. All right, so, are we okay so far? All right. Why will a tuning fork cause an identical tuning fork nearby to resonate? Okay, so I showed these to you at the beginning, but just to grab your interest, at the beginning of the unit, they are tuning forks, and when I strike them, there's a vibration that's directly connected through where this tuning fork is mounted to under the box or inside of the box, and it kind of focuses the sound. So you can hear that? Okay. This tuning fork, and when it's a little bit loose. When I touch it, I damp out all the vibrations, so you can't hear anything. This tuning fork is identical to this tuning fork. The frequency of that tuning fork is identical to the frequency of this tuning fork. Okay? And how is that possible? Well, they're made of the same material, they have the same shape, they have the same mass, they're the same size. They're identical in structure. And that's how you make tuning forks. You put certain weights on the tines, or you change the shape of them until you get the frequency you want. Okay? So the idea here is that if I put one tuning fork on this side of the room and the other one on this side of the room, and Sydney, can you just verify that there's no sound here? Okay. And then I strike this tuning fork. That tuning fork is making a sound now, isn't it? Yes? No? No? Yes? Very faint, but it's there. I mean, it's there. I don't want to pass this around the room. We can play around with it tomorrow when we have more time. I mean, to make it more apparent, I'll put them right next to each other. They're not physically touching each other, although I guess they kind of are because they're both on the same desk. So maybe we'll do this. And I know you could argue that they still are because they're on the floor. They're on desks that are connected with the floor. But I don't think the floor is going to vibrate. Okay, it's acoustic that's happening here. Is it vibrating? Like you can hear it? I like that you put your hand there. Like you would never, I don't think you'd feel it, but you can hear it. Yeah? Okay. So why does that happen? Well, because there's a physical connection between them. Sorry. There's a physical connection between them. This tuning fork on your left is in direct contact with the air, so however many times per second it vibrates, the air will vibrate at that same frequency, causing the air next to the other tuning fork to vibrate at the same frequency, which it can because it's the same tuning fork. So basically there's a physical connection between tuning fork A, or 1 I guess, and the air, and a direct connection between the air and tuning fork 2. If I change the frequency of one of the tuning forks, and I'm going to do that by putting 2 magnets on the tops of the tines, which is going to make the tines heavier, which is going to change the frequency. And I will demonstrate to you that the frequencies are different. The app I have on my phone is not perfect. I didn't bring the mic to attach to it, but I have an app on my phone which will read a frequency. So Colin, you're going to just help me out here. So we're looking at this frequency, and it's bouncing all over the place because my voice is, it's versatile. It has many different frequencies. So I'm going to strike this tuning fork near my phone.
248.
Say again?
Like 247, 248.
So it's going back and forth between 247 and 248. What about this other tuning fork, which I haven't messed with?
259.
259, 260. They're different frequencies. So even if I put them right next to each other, this tuning fork will not make a sound now because they don't have natural resonant frequencies that are equal. Just like if I'm not traveling at exactly 106 kilometers per hour, my dash will not bounce up and down. Okay. Are we okay with resonance? Now we're going to talk about beats. And this is the last thing we're going to do today, so my timing is going to be okay here. I just want to demonstrate what beats are and how to calculate beat frequencies, but we're not going to explain why beat frequencies are calculated the way they are. It's very complicated. So I've already told you that if these 2 tuning forks are not identical, then resonance will not occur. Okay, and these 2 tuning forks are not the same. I'm going to put these magnets down here. That's what that thing is. I saw this little rubber thing on the floor. There it is. These 2 tuning forks are not identical, and I don't want to get into too much detail about this, but can you appreciate that if I put these magnets up top, I'm probably really going to change the balance of this tuning fork a lot? Whereas if I put them down here, it's not going to change the frequency that much. So I would hope you would agree that these 2 tuning forks have different frequencies right now, but they are close to being the same. So if I sound one, it will not cause the other to sound, and if I sound the other, it will not cause the first to sound. But what if I sound them at the same time? again, a little lighter. That annoying high-pitched vibration you hear, I think is the magnets moving around on the metal. Okay? How many of you notice that it's going up in volume and down in volume very slowly? I can make it more apparent by changing the frequency of the other tuning fork by even more. I think that's pretty obvious what we're looking at here, or what we're hearing here. Those are called beats, and I would say that the beat frequency here is about 2 beats per second. I think it's less than 2 beats per second, but it's more than 1 beat per second. Let's call it 2 beats per second. What happens if I change the frequency of the first tuning fork by even more? So now, at 2 beats per second, the frequencies were this far apart. Now the frequencies are going to be really far apart. More beats per second, yes? I would say 5 to 6 beats per second. I mean, I don't know how my brain is processing that, but I'm hearing approximately 5 beats per second. And it turns out that the number of beats per second you hear will be the difference between the two frequencies. So I'm going to use my phone again to measure these frequencies. What did I say, about 5 beats per second? Would you agree? I mean, I don't want to... That wasn't a very good one, was it? I would maybe go 4 beats per second. So what I'm going to do is I'm going to attempt to measure each of these frequencies. Well, that's at 259, 260 that we talked about for this one. So let's call it 259 or 260. I can write that down. I'm just writing down both numbers because the app on my phone is just wobbling back and forth between them. And when I take a look at this one, $252, $253. Now keep in mind, I estimated 4 beats per second. This is closer to like 7 beats per second. There's a difference of 7 there. So that's what a beat frequency is, and that's how to find it. It's very complicated for me to explain to you why we subtract the two frequencies. Okay? We're going to do 2 quick examples here dealing with beat frequencies. Basically what's happening is, and I'm going to go to this one, this example. Basically what happens is if I have a wave with a frequency of 4 hertz, it's producing compressions regularly 4 times per second. And if I have a second wave with a frequency of 5 hertz, notice I'm saying wave because I wouldn't call these sound waves. You would never hear this. If my second wave is at 5 hertz, it's making compressions 5 times a second. So there's an overlapping of when the compression of one meets the compression of the other, and it turns out it's going to happen 1 time a second. On the other hand, if it were 4 hertz and 6, it's going to happen 2 times per second. Are you with me on that? So we can answer this question. The beat frequency would be 1 hertz here. And the beat frequency would be 2 hertz here. I don't know if there are too many people that still do this, but I have a piano and I used to hire this guy to come out and tune my piano every year. He's an old guy. And he was old school. He would open up his case and he would have all these tuning forks. And what he would do is he would hit the key on the piano, which hits a string inside the piano and makes a noise called sound. It's a note. And he would take the tuning fork that sound is supposed to match, and he'd always hit it on his knee. And he would listen. And if he heard a beat frequency, then that string needed to be tightened or loosened. Because if he heard a beat frequency, then those two frequencies were different. And he knows the tuning fork is correct. So if he heard a lot of beats per second, that would mean the frequency of the string is way, way far out. And if he started tightening the string and he heard even more beats per second, he would know he's going the wrong way and he would loosen the string. Of course, now you guys know there's little electronic things, right? Well, my phone, you just put it there. You'd put it next to the string and you would tighten or loosen the string. One final question, and then I want to end today with a demonstration. What if the frequency of one of the tuning forks is 250 hertz, and you hear a beat frequency of 3 hertz? If I just asked you what is the frequency of the other tuning fork, you should say there's 2 possible frequencies. If the beat frequency is 3, that means the second tuning fork differs from the first by 3 hertz. It could be 3 hertz more, or it could be 3 hertz less. So F2 could be 247 hertz or 253 hertz.